So dear ladies and gentlemen, exploring the planets, moons and small bodies in our solar system allows us to get a glimpse into our own origins. Asteroids are key objects to investigate the formation and evolution of our solar system. But at the same time, we also want to study their properties, since they may present a hazard upon impact. So JAXA's asteroid sample return mission, Hayabusa2, was launched in 2014 and first observed the object Ryugu from orbit before depositing several landers onto the surface. And one of those landers was the German-French landing module Mascot, which provided new insights into the structure and composition of asteroid Ryugu. JAXA's Hayabusa2 mission has successfully collected and returned samples from asteroid Ryugu and the capsule touchdown in Australia in December 2020. The IAF is proud to acknowledge the Hayabusa2 team as winner of the IAF World Space Award 2021. The Hayabusa team has greatly contributed to the advancement of robotic interplanetary sample return missions through a series of flawless operational accomplishments made possible by its sophisticated technologies concerning solar electric propulsion, cruising, landing, roving, impacting and returning to Earth with asteroid material. So I'm delighted to call on stage Dr. Juji Tsuda, professor at the Institute of Space and Astronautical Science and project manager of the Hayabusa2 project at JAXA, to give the highlight lecture.
Good evening, and welcome to the highlight lecture of this evening. And I'm very honored to speak in front of you as a highlight for the highlight lecture of the IAC 2021 Dubai. And this is a talk about Hayabusa2, the Japanese sample return mission, which just completed the last year. And we had actually a nice highlight lecture the day before yesterday by the OSIRIS-REx mission, which is another sample return mission run by NASA, and which is now on the way back to the Earth. But this is the talk about the Japanese version of the sample return mission. And yes, now we are in the era of bringing the sample from the other celestial bodies back to Earth for direct and physical analysis of the material there. So it's really a significant and effective way of doing space science, and also very difficult, challenging, but interesting and exciting way of doing the space mission from the viewpoint of engineering. So I hope through this talk you can feel how interesting, how challenging, but how fun to do this kind of mission. And I'm Ryugu from JAXA, and my background is the astrodynamics in the Institute of Space and Astronautical Science, ISAS, which is Space Division of Space Science Division of JAXA. But for this Hayabusa2 mission, I have been served as a project manager of the project, of the mission. And today I'm going to cover the whole story of the Hayabusa2 mission, operation results, and the significance of the small body exploration or sample return mission to the small bodies. And actually, let me first excuse, as I'm not a good English speaker, so please allow me to use the manuscript that I prepared, as I won't tell you the wrong information, or maybe I may sometimes exaggerate what I did. So anyway, I may exaggerate my emotion because I cannot stop being excited when I talk about the result of the Hayabusa2 always. But manuscript reading is not, it is good for preciseness, but probably not the best for making you excited. But I guess in this world, you're a professional or expert of the space science or space engineers, so you are familiar with the interpolation technique. So please interpolate my talk with your emotion. Okay, so let's start. Or probably you can use the extrapolation if you like, but only to the positive direction, please. Okay, so let me first start from this movie. This is the movie recorded by the Hayabusa2 onboard sampler home monitor camera at the time of the second touchdown. This is the moment of the final freefall descent from 8.5 meter altitude and then touched the ground, retrieved the samples, and ascended away. The notable thing here is that this is the second touchdown. It means that we did 2 landings to 2 different sites on the asteroid. Moreover, the second touchdown tried to get subsurface material, and I will touch about this later in more detail, later. And surprisingly, even to us, the landing position error was as small as 60 centimeters. Thinking about the distance between the Earth and the spacecraft at that time was about 300 million kilometers, which corresponds to 20 minutes one-way lifetime time. So this level of accuracy was more than enough and satisfactory enough. And although we faced many hardships during the asteroid proximity operation, we overcame all, and Hayabusa2 finally returned to Earth last year. This is a landed re-entry capsule with the parachute deployed on the lunar desert south of Australia. Okay, so before going into the main story, let me slightly mention about the history of the Japanese space exploration. This chart is summarizing the Japanese lunar and planetary mission program. The first planetary mission or deep space missions of Japan were Sakigake and Suisei, launched in 1985 to Comet Halley. These missions were followed by Hiten, which went to the moon, and the Mars Explorer Nozomi, which unfortunately failed to be inserted to Mars orbit, and then Hayabusa, which became the world's first successful sample return from asteroids. And in 2010s, we embarked on planetary missions to various celestial bodies, such as Kaguya to the moon and Akatsuki to Venus, and also a tech demo mission, Icarus, which achieved the world's first interplanetary solar cells technology. Then the follow-up mission to Hayabusa is Hayabusa2. We also have multiple ambitious missions in 2020s, including landing on the moon, Mars-Moon sample return, and then the Comet high-speed flyby, and so on. So Japan has a long history and the experience of the interplanetary science missions. Although the number of missions is not so high, the program has efficiently and effectively contributed to the evolution of both spaceflight technology and also space science. Okay, so about the Hayabusa2. Hayabusa2 is the second sample return mission for us. And the first Hayabusa went to asteroid Itokawa, which is an S-type or stony asteroid. On the other hand, the target of Hayabusa2 was selected among several, actually not so many, C-type asteroid candidates which were accessible with our present technology. The C-type means carbon-rich, or the carbon is an indispensable material for life on Earth. And in fact, Ryugu was estimated to contain the organic compounds and hydraulic minerals by the ground telescope-based observations. The Hayabusa2 aimed at the science to explore the history of the solar system and also the clue to the origin of life by bringing carbon and water-included samples of Ryugu back to Earth. So the key feature of the Hayabusa2 mission are listed here. It's a round-trip mission enabled by high-specific impulse ion engine combined with the continuous thrust trajectory control technique. And also, our plan was to stay in the proximity of the asteroid for 1.5 years, doing the proximity operation using 4 mobile rovers and 4 in-situ observation instruments, and more other instruments. And the main highlights of the spacecraft of the mission is, of course, the touchdown. So in the original design of Hayabusa2 spacecraft, it was capable of doing 3 touchdowns. Out of 3, 2 were the normal touchdown, which are the direct heritage of the Hayabusa1 technology. And the third one, what we call the Pinpoint Touchdown, was to aim at a very precise landing in the vicinity of the artificial crater, which I will mention later. But in reality, because we faced very severe environment of Ryugu, we decided to do the touchdown twice, but applying the Pinpoint Touchdown from the first. And even we modified the original Pinpoint Touchdown to adjust to the environment of Ryugu, and we succeeded. And the another attempt, the challenging attempt we did is the artificial crater forming. And we basically use the technology called Kinetic Impact, and we accelerate the 2 kilogram pure copper to 2 kilometers per second and instantaneously, and form a crater on the surface of the asteroid for the subsurface investigation. And we succeeded in actually making the 18-meter diameter, very big artificial crater on the surface, and even touched down in the vicinity of the crater to get the subsurface soil. So the mission scenario of Hayabusa2 goes like this. It's a 6-year mission, launched in 2014, and after 3.5 years of the interplanetary cruise, we arrived at Ryugu in June 2018, and we stayed there for 1.5 years, doing many challenging operations. And on November 2019, we left there for the Earth's return in December 2020, last year. The appearance of the Hayabusa2 spacecraft looks like this. It's a very compact spacecraft having only about 600 kilogram wet mass. The tip-to-tip span of the spacecraft is 6 meters, and Hayabusa2 is a solar electric propulsion spacecraft. It is equipped with a high-specific impulse ion engine system with 66 kilograms of xenon fuel, which corresponds to about 3 kilometers per second orbital maneuver capability. And thanks to this technology, we could carry as many as 14 scientific instruments to cover various types of in-situ exploration activities packed into this very compact spacecraft. And one of the interesting features engineering-wise actually I'm an engineer, so I'm excited about this kind of things. And is that the Hayabusa2 brought as many as 12 deployables to space. Rovers, lander, kinetic impactor, artificial navigation landmark called target markers, and so on. And here I now show when they are separated, detached from the spacecraft. Most of them were separated around Ryugu, except for, of course, the sample return capsule, which was separated toward the Earth. And the Hayabusa2 mission was realized under the very successful international collaboration. In addition to more than 200 scientists from Japan, we had more than 200 scientists from international communities, as Ryugu had never been explored before, and sample of C-type asteroids had never been handled before. So it is the most effective way to have tight collaboration within the worldwide academia to maximize the scientific outcomes. And we also have the tight collaboration with NASA, DLR, and CNES, and ESA, as well as Australian government and the Australian Space Agency. We could not have succeeded in this ambitious endeavor without support from these international friends, and without this very nice international teamwork. Hayabusa2 is a solar electric propulsion mission combined with the Earth's gravity assist. The total acceleration for the trajectory control was about 3 km per second, but out of it, 1.6 km per second was assisted by the Earth's gravity assist. So thus the required delta V for the ion engine alone was 1.3 km per second, and it took 3.5 years for the forward trip and just a year for the return trip. The Hayabusa2 arrived at Ryugu on June 27, 2018, about 3 years ago. The appearance of Ryugu was very interesting, full of new discoveries, scientifically and hopelessly harsh environment engineering-wise. It was revealed to be a top-shaped asteroid with a diameter of about 900 meters. It's about twice as large as the asteroid Bennu, which is the target of the NASA's OSIRIS-REx mission. The Ryugu has a retrograde rotation with a period of about 7.6 hours, so 3 times faster than the Earth. The Ryugu is a very dark asteroid having only 2% reflectance factor. And this very dark, low reflectance surface property actually caused several errors and operational aborts in some of the critical operations of the Hayabusa2. But there was a worse source of headache in Ryugu. The biggest headache for us was, if you look at the surface of the Ryugu, you can see many, many boulders all over the globe. What we have said is that it's a homogeneously bumpy asteroid. So this forced us to change our strategy for the landing operation. And we were obliged to improve our landing performance from the original 50-meter accuracy, 2.5 sigma, to 1-meter accuracy. And one of the exciting part of the mission is we have many international colleagues to discuss with. This is a photo from one of the project's most critical meetings held after the arrival to select the landing site candidates for the spacecraft and 3 rovers. For this meeting to be successful, we had done data analysis and decision-making training for 2 years before the asteroid arrival, making sure that teams from different countries and groups could handle the same data in a right way, exchanging quantitative and very delicate data analysis results appropriately, and to be able to reach the consensus quickly. This landing site selection meeting, or LSS meeting, was held just 1.5 months after the Ryugu arrival, so it's a very quick process, and participated by more than 100 scientists. And we could derive a set of landing site candidates very smoothly. The only one element which was not smooth was the terrain of Ryugu. So the human side is very smooth, but the asteroid was not smooth. Therefore, we imposed ourselves a lot of homework after the LSS meeting, mostly to refine our landing accuracy to adjust to the Ryugu environment. So this is a scene from the press conference right after the LSS meeting, and the leaders of the Hayabusa2 project are all here, including from the left, Dr. Aureli Musi from CNES and Trami Ho from DLR. Those two are the project managers of the mascot lander, and also the project scientist, Dr. Watanabe. So we held this kind of press conference every 2 weeks during the proximity operation phase, and for each press conference, key scientists and engineers attended to explain about new findings and new plans, sometimes the challenges and difficulties we are facing. So you know, a space agency usually doesn't like to tell about the uncertainty or failure probability of the ongoing project, but we try to the press conference to be a place to make general public feel a sense of togetherness by disclosing our challenges. So this really helps stimulate the general public, and I think Hayabusa2 mission was so successful also from the aspect of the public relations. So based on the conclusion of the LSS meeting, we first deployed 3 rovers, actually 2 rovers and 1 lander. The first 2 were a Minerva 2-1, which is on the left top, and it is a twin rover separated at once. And the second one was a mascot, which is in the right top movie, which is a 10-kilogram box-shaped lander developed by DLR and CNES. These 3 rovers moved around the Ryugu surface at once, controlled from the ground station through the Hayabusa2 model spacecraft. And they could get these kind of close-up images of the asteroid surface. You can see a black world full of boulders and rocks. The rover's scientific instruments were not only camera, but also includes temperature sensors, magnetometer, infrared spectrometer, and so on. And here's an example of how we operate the mascot lander, which was actually one of the most complicated operations of the entire Hayabusa2 mission, involved by many different ground segments. As the lander was equipped with only a primary battery, which could last only for about 16 hours, everything had to be scheduled and efficiently allocated. The mission control of the mascot was in Cologne, Germany, and the command telemetry was connected through the Sagamihara Space Operations Center in Japan, and also deep space stations provided by JAXA, NASA, and ESA. The mascot landed on Ryugu October 3rd. It's actually the time that the IAC Bremen was held, so it's really a very optimum coincidence, but with the upside down orientation. The mascot team immediately commanded the hopping, which successfully flipped the orientation of the mascot to an appropriate attitude. And after the mascot could observe the surface for 2 full asteroid days, with 1 additional bonus day, 17 hours in total on the surface of Ryugu. And all in success, mascot team declared the mission completion. So, the rover operations were all successful, and now the problem is, how can we land the spacecraft to Ryugu? As we increased the resolution of the observations, we got to know more the severeness of the terrain environment. The original specification of Hayabusa2 was that the landing accuracy 2.5 sigma was 50 meter, which means that we needed at least 100 meter diameter flat surface on Ryugu for safe landing. We found it was unrealistic for Ryugu. But still, we had to find a place to land because Hayabusa2 is a sample return mission, so returning without sample is not an option. So in fact, this process took about additional 6 months. Let me skip the step-by-step process as time is limited today. Finally, we found the 20-meter safe place, which was shown in the right bottom, the orange circle in the figure. So you can see in this image that just outside the circle, there are many big rocks, but within the circle, the surface looks relatively flat. But the diameter of the circle is only 20 meters, which means that the landing accuracy must be less than 10 meters. It was beyond the original performance of Hayabusa2, so we planned to do an experiment to measure our actual performance. For that, what we decided to do was to drop an object to the ground instead of the landing the spacecraft itself, and evaluate how precise we can physically place an object to the Ryugu ground. And for that, we use the target marker. So the target marker is a 10 centimeter reflective ball illuminated by the flashlight at the bottom of the spacecraft. It works as a visual landmark. And Hayabusa2 was equipped with 5 target markers, and we used one of them for this experiment. And we tested the landing accuracy by dropping the target marker to a target site instead of landing the spacecraft itself by using the same guidance scheme. And the result is here. So this is the picture of taken after the target marker drop. So can you find a target marker from this image? It's actually here. So I think it's difficult for most of you to find a target marker, but Hayabusa2's image processing can precisely detect it. We threw the target marker to aim at the center of the 20-meter orange circle, and the result was that the target marker was settled 15.4 meters off from the center. 50.4. It was actually a very good result compared to our expectation of like 50 meters. So engineers were somewhat happy about this result. But this result means that the landing precision is not sufficient to conquer Ryugu. But there was one more good news actually. We actually attempted another guidance test in this target marker drop experiment to chase the dropping target marker using the onboard autonomous guidance system. So I will show you here. So you can see a bright dot, which is the dropping target marker observed from the onboard navigation camera. As the spacecraft is trying to chase the target marker by lateral thruster firings, the target marker is eventually converged to the red target control box. The corresponding size of this red box at the terrain level was 1 meter. So this means that regardless of the terrain condition, once the spacecraft can detect the target marker, it can precisely locate and guide itself with a terrain relative accuracy of less than 1 meter. So it's a really, really good news for us. So now we got the confidence for the target marker tracing capability. So we decided to make a full use of the target marker to realize what we call the improved pinpoint touchdown strategy. Originally, we didn't think to use a target marker like this. The original plan is actually on the left of this chart, and the modified plan is on the right. Originally, target marker was to be separated from the spacecraft just before the touchdown during the final descent toward the ground. The purpose of it was to completely eliminate the terrain relative velocity at the touchdown, which was essential for the safe landing to unknown terrain. However, based on the successful result of the target marker drop experiment, we changed the strategy to utilize the already dropped target marker as the visual landmark. For that, we survey the terrain around the dropped target marker and find a safe place. Then, using that target marker, the spacecraft tries to land on the found safe place using the target marker as a landmark. So now the problem is there a safe place near the target marker? So this is the mosaic images around the candidate landing site captured by the Hayabusa2 onboard camera. Here is the dropped target marker. Here's the target marker. And you can see many circles and values on the image which show the height information of the rocks in centimeter. And because of the length of the sample horn is 1 meter, and the rock should be smaller than like 70 centimeter or so. And red and pink are dangerous rocks, and yellow is a marginal or warning level, and blue is a safe rock. So to use the target marker as a visual landmark, the landing target should be as close as possible to the target marker. So where do you think is the best place to land? So our conclusion was like this. So we found two candidates actually. One is within the original 20-meter circle, and now drawn with the red zone. It is about 15 meters away from the target marker, but the size is relatively large. Another one is a green zone, which is only 4 meters away from the target marker, but has only 6 meter diameter. And our conclusion was to choose the green one. Although it is very narrow, having just the same size as the span of the Hayabusa2, but we evaluated that we could achieve less than 3 meter precision landing to the green zone. On the other hand, the red zone was a little bit too far, and landing accuracy to such far distance would get very bad. And the resulting sequence became like this. The onboard guidance computer of the Hayabusa2 is fairly flexible and is equipped with a kind of high-level programmable sequencer. And we rewrote it to implement this sequence. At the round-trip flight time at that time was 40 minutes. Ground-based guidance is not possible at all. So everything has to be autonomous. At first, spacecraft hovers at 45-meter altitude and find the target marker. And once target marker is found, the spacecraft is to dive into 8.5-meter altitude, tracing the target marker. Then, because we want to land not on the target marker, but 4 meters northeast of the target marker. So Hayabusa2 is to move horizontally while looking at the target marker. And then, after everything is converged, it is to make a final free fall to the landing point. And we uploaded this new sequence to the spacecraft and sent a go command to the spacecraft on February 22nd, 2019. Okay, so let me show you the actual result. I'm sure space engineers in this floor love this kind of movie. So this is a movie. Is it playing? Okay. This is a movie about target marker relative guidance at the touchdown, actually used for the onboard real-time navigation. The target marker was detected at the altitude of 45 meters and descended to 8.5 meters. Because our aim is not to land on the target marker, but to a place 4 meters off from the target marker, so the onboard guidance computer changed the target like this, and so that the onboard, the target marker should be placed in the edge of the FOV of the onboard camera, and in this way, Hayabusa2 could go right above the target landing point precisely. And this is the actual movie of the final freefall and landing from the first touchdown operation. The sampling process was all successful. At the moment of the touchdown, the projectile was ejected and some portion of the reflected samples are collected and through the sampler home and finally stored in the sample container located at the root of the sampler home. This is actually one of the loveliest movies for me, obtained throughout the entire Hayabusa2 mission. So now, we succeeded. So is it now the time to return to Earth? No, Hayabusa2 story is still before the climax. Okay, let me play it again. Okay, so just 1 month after the success of the first touchdown, we attempted another ambitious mission, the Kinetic Impact. Device called the SCI, or Small Carrier Impactor, is separated, and this will soon detonate. And before that, Hayabusa2 rushed to the backside of the Ryugu to avoid damage by the explosion. And then SCI detonates and makes an artificial crater. This system can accelerate a 2 kg pure copper bullet to 2 km per second instantaneously. The reason why we used copper is we don't want to contaminate the sample, as we may plan to collect the soil sample from the artificial crater afterward. And because the spacecraft has to escape, it cannot observe the impact process. So it's a pity. So on the way of escaping, Hayabusa2 deployed a remote camera called DCAM-3. It's like a single-use disposable camera, only to shoot the cratering process. And before damaged by the impact fragments, DCAM-3 transmitted the image data to the mother spacecraft. And it was actually really acrobatic operation, and we succeeded in getting this kind of beautiful movies. You can clearly see the big impact process. The impact ejector could be observed for more than 5 minutes. So it's actually a very slow process. And height of the ejector reached up to 40 meters, so it's a very big reaction. Furthermore, the spacecraft could go back to the vicinity of Ryugu again and observe the terrain, compare the terrain before and after the impact. Scientifically analyzing the impact response led to deriving the cohesive strengths of the asteroid surface, which in turn resulted in deriving the surface age of Ryugu. It was derived and published on Science that the original theory suggested 160 million years surface age, which was overwritten, corrected by the experiment to 10 million years. So the surface of Ryugu is actually very young and variable. So as soon as you do something like this, the TV stations want to make a full-scale set. So this is a full-scale set of the artificial crater based on actual digital elevation map made by Japanese broadcasting company NHK. The diameter is 18 meters and the depth is 3 meters maximum, and you can feel how big a crater we created. And the next thing we wanted to do was, of course, why not dive into a crater we made to get the subsurface material, like this. In reality, it was too risky to make the spacecraft dive into 3-meter hole. We tried to find a safe place to land around the crater where a rich deposit exists. So we found 2 options at that time. The first option was what we call the S01 region, which is smooth and safe for landing but with less deposit. The second option was C01 region, which is here, which was bumpier than S01, but obviously a thick deposit exists there according to thorough observations by multi-band cameras. We had a lot of discussion from the viewpoint of science, technical feasibility, and management risk. you have to go back to Earth with sample. If we fail in the second touchdown and lose the spacecraft, it means we also lose the samples from the first touchdown. On the other hand, the scientific value of the subsurface material and scientific value of the samples from the multiple places are enormous. So, and it was also a question of the risk of challenging versus not challenging, and how we, actually not so big institute like ISAS, can contribute to the planetary science of the world. And eventually we could decide to do the second touchdown to C01. C01 was actually here. Yeah. And we evaluate, the circle is a 7-meter diameter region, which is slightly larger than the first touchdown landing zone. So we evaluated it was technically feasible and the risk for it was acceptable enough. And besides that, it is the scientifically best place to sample. Like this. So please look at the movies while landing in the control room. This is before COVID-19, so many people are in the control room, and it's really one of the best time for us. So now, again, is it the time to return to Earth? No, not yet. Hayabusa2's challenge does not end yet. So after the second touchdown, we did another very delicate but scientifically important operations, putting 3 objects onto orbits around Ryugu to contribute to the gravity science. As at that moment, 3 target markers were still left on the spacecraft, and we put 1 target marker to an equatorial orbit around Ryugu, and another to a polar orbit, and also we put the 4th rover to another equatorial orbit around Ryugu, which were all successful. So this is showing the entire proximity operation activities, and it was really a very busy period for us, and we did critical operations almost every 2 weeks. I already talked about the rover landing, spacecraft landings, and so on, but to realize it, we needed to do additional critical descent operations for surface high-resolution surveys and for guidance rehearsal. Also, besides such critical operations, we did many scientifically important observations from the high altitude, like moving to the side of the asteroid for terminator observations, or observing the polar orbit, the polar region of the asteroid. And as a result, we did all the operations almost as planned in terms of the fuel consumption or number of the descent operations. And we did 2 landings, 4 rover delivery to the surface, 1 artificial crater forming, and in addition, 3 objects were inserted to Ryugu orbit, which was not in the plan originally. And as we explored the Ryugu, we named the geological features. As the asteroid name Ryugu was named after a famous fairy tale from the ancient Japan, so we named some of the geological features based on the world's fairy tale, like Urashima Taro, Cinderella, Alice's Wonderland, and so on. And 7 craters, 1 dorsal, 2 fossa, and 3 saxa were named and authorized by the International Astronomical Union. And we also gave nicknames to some of the landing points of the spacecraft and rovers. Although they are too small places to be authorized by IAU, they are very important places for us. And after finishing all these operations, Hayabusa2 departed Ryugu on November 13, 2019. And these are the sequence of images taken while leaving Ryugu, so the final shot of Ryugu. The left movie was taken by the telescopic navigation camera, and the right movie was taken by the wide field of view camera at the same time. After this, we turned off the cameras and turned on the IO engine and started heading to Earth. So this is the last picture of Ryugu for the Hayabusa2. And after leaving, the return cruise took about 1 year. The last 2 months required very precise guidance so that the spacecraft should land to a designated landing zone in Ulmer Desert, Australia. The return capsule was separated from the spacecraft 12 hours before the re-entry, and it flew ballistically toward the atmospheric re-entry corridor. And 1 hour after the separation, the spacecraft itself diverted from the re-entry orbit so that it could escape from the Earth's sphere of influence and continue to the extended mission. So this movie shows how we did the re-entry operation. The capsule was separated about 220,000 kilometers away from the Earth and 12 hours before the re-entry, and then the spacecraft diverted from the re-entry trajectory for escaping. And meanwhile, the spacecraft capsule will make up Earth's re-entry like this. And at the altitude of 10 kilometers, the parachute is deployed and landed softly on the ground. And in parallel with the space side operation, we had to deploy about 100 people to Australia to retrieve the capsule. It was right at the time of the COVID-19 pandemic was growing. So, but the Australian government and the Australian Space Agency were so supportive to our mission and smoothly accepted our team to Ulmer Desert. So please watch a short movie about the capsule recovery team activities in Australia and beyond. So after bringing the capsule into the curation facility in JAXA Sagamihara, we opened it and found 5.4 gram of Ryugu sample there. Our mission criteria was 0.1 gram, so it's far more sample than expected. As the sample container consists of 3 isolated chambers, samples from 2 landings were stored separately. Today, I'm not in a position to say anything about the results of the detailed sample analysis result, but we already confirmed it contains organic compounds. And we also detected a trace of a reaction with water in the samples. The detailed analysis is still ongoing, and I'm expecting we can say something in a few months. So I am looking forward to the result too. And in the first 6 months after the Earth's return, the sample was handled only in JAXA curation facility for initial description process. In June this year, the analysis transited to the phase 2 curation and the initial analysis phase, where the sample was analyzed in several specifically selected institutes. From the end of this year on, we will start to deliver some portion of the sample to the international community. We will exchange the sample with NASA's OSIRIS-REx mission, and for that we are preparing to deliver 10% of the sample to NASA in the end of this year. In the next year, we will open the international AO to deliver a part of the samples to general researchers. And also we will store 60% of the sample for future generations. The Hayabusa2 spacecraft is still healthy as I explained. After separating the re-entry capsule, Hayabusa2 continues its flight to head to 2 new asteroids, 2001 CC21 to fly by in 2025, and 1998 K126, which is a very small fast rotator asteroid, and to rendezvous in 2031 as an extended mission. So this extension should contribute not only to the new science in the new asteroids, but also to planetary defense technology and science. Hayabusa2 mission was a perfect success, not only fulfilling all the mission objectives defined beforehand. We accomplished several engineering successes which had not been expected, partially thanks to severe environmental Ryugu. We succeeded in multiple rover activity on the asteroid surface, multiple landings and sample collection, exploring subsurface, orbiting, and then returning samples from the new world. And the Hayabusa2 was successful also from the aspect of outreach and public relations. We did many outreach activities unique to sample return mission, such as naming the asteroid, imagining Ryugu contest, which is the compete for how precise one can predict the shape of the asteroid before arrival. And we had many of the funny asteroid shape before arrival. And we also did several Ryugu and Hayabusa2 observation campaigns when they flew close to Earth. And we gathered more than 800,000 views for the touchdown live stream through YouTube and more than 300,000 followers of Twitter worldwide. And the significance of the Hayabusa2 mission is summarized with these keywords. What Hayabusa2 realized was various types of activity in the vicinity or on the surface of the asteroid. Hayabusa2 attempted not only accessing to the vicinity space around Ryugu, but also interacting physically with the celestial body by roving, sampling, and impacting on the surface of Ryugu. It must be a tiny step if viewed from people 100 years later, but it is a definitive step toward in-situ planetary exploration capability, and I'm sure this would contribute to science, space exploration technology, planetary defense, and planetary resource of the near future. Okay, so actually this is I have 2 more slides. Last year, there was another big news from another sample return mission, OSIRIS-REx of NASA. We have been in a good collaboration with OREX team for a long time. And when both missions arrived at the target asteroids, we were so surprised that two asteroids are very similar to each other. And the colleague from OREX team asked me, did you really arrive at Ryugu? I answered, I promise it is Ryugu. I calculated the trajectory of Hayabusa2 by myself and did not do such a terrible mistake. But anyway, OREX succeeded in landing and sample collection last year. But before that, they faced very similar problem as ours, because Bennu is very bumpy asteroid, just as Ryugu is. So let me tell you a small story. So we had a joint science meeting after the Hayabusa2 succeeded in the touchdown and before OREX attempted the landing. And there I talked with Dante Roletta, the PI, principal investigator of the OREX mission, and he said, if only OREX was equipped with target marker. As they don't have such equipment, they applied the natural feature tracking, which seems more sophisticated and difficult than the target marker-based guidance. The target marker is artificial, so relatively easy to process by onboard autonomy, but natural feature tracking has to deal with natural feature, which is apparently more difficult. They finally succeeded in it, which was really incredible. However, at the chat, I responded to Dante. Oh, my thought was other way around actually. What I thought is, if only Hayabusa2 was equipped with longer sample horn, like OREX sample arm. Then our conclusion was, let's make the next generation small body sample return spacecraft together, which is equipped with target marker and longer arm. So this is exploration. This is a challenge to unknown. So we cannot know how much length of sampling arm we need before we actually get to the asteroid. And we cannot know how effective the target marker is beforehand. I'm so pleased that Hayabusa2 could demonstrate the big possibility of our technology, and I strongly hope that more ambitious and more scientifically valuable missions will be born based on the Hayabusa2 achievements. So Japan has several plans in 2020s, a mission to Mercury, which is already ongoing, and an extinct comet flyby, Martian moon sample return, and lunar landing. So we do not have an authorized plan for 2030s, but we hope to grow our sample return exploration technology more to the outer region of the solar system. So with that, I would like to conclude my talk. Thank you very much for the honorable award, and thank you very much for your kind attention.
That works, yeah, that works. So this was a fascinating lecture, and I think the thing what you really have to take with you is that we are going to an object and we have no idea. It is really the unknown, and we are trying to see how we can land. And I think you really made it very clear how difficult all the decisions are when you are going to an object which is unknown, and that every object which we approach, we first have to scout and we have to learn what are the possibilities. And if you would have actually made the maneuvers very early, you would not have the result which you probably have now. So it is a first, and I think also the next mission has learned a lot from you, and it was great that there were some smaller landers to scout, and because the surface has been completely different than everybody thought. So I know it is very late, we are a little bit over the time, and I forgot actually to put the Slido. So I just wanted to make it rather easy, and if there are questions, maybe you can answer them from here, and I will go, or from here as you like, and we will give the microphone into the audience. That would probably be easier. Are there any burning questions? Then please raise your hand, and we are going to come with a microphone. Yeah. Okay, we have one.
Yes, so you mentioned that you found some organics. So can you unveil some special interpretation? What is the significance and what we hope to learn from the organics you found in the samples?
Okay, so we already analyzing the chemical, what kind of chemical compound is included in the sample, and we identified that it is the organic compound, but we still not yet determine what type of molecular structure that they have. So actually, I cannot say anything about that this time, but for sure we have evidence that it is in the past reacted with the water. So it may mean that the water is included in the sample with the organic compound, or maybe reacted sometime in the past, in the early era of the Ryugu. We are not sure about that yet, but for sure we can say something.
Okay, so in IAC Paris, we will know more. So
yes.
A lot of world technology first presented here, and then we'll hear some of the world scientific first. Thank you very much. Congratulations to the team.
Thank you.
So my question is about an engineering aspect that wasn't on the presentation. How did you actually manage to put the samples that you have extracted into the lander? What was the mechanism inside? How did you do that? If you could shed some light upon that.
You're asking about the separation mechanism?
Not exactly, because as I have understood, you had the arm that extracted the samples, and then you had to put it somehow into the lander that landed on Earth.
Lander, the re-entry capsule.
Not exactly about the process, how it was done inside the satellite, that you took the samples from the arm that extracted them and put them into the lander. What was the mechanism? Just wondering.
The re-entry capsule. Yes. Yeah, the sample is collected by the sample hole by the ejection of the projectile, and the reflected soil is moving upward to the root of the sample hole, where there is a chamber which stored the sample. And after that, there's an internal mechanism which transport the chamber laterally to the re-entry capsule. And after that, there's another mechanism to close the re-entry capsule, and then after that, right before the re-entry, the re-entry capsule is separated. So there's an actually very complicated mechanism inside the spacecraft, which is based mostly on the non-explosive actuators.
Hi. I just wanted to ask that why was it chosen to use short payloads as detonators to create artificial craters on the asteroid, instead of just sending the lander down itself and attaching itself to the asteroid to maybe drill it down and get some samples from inside? What is the ideology behind that?
About the crater?
Yeah.
Okay, yes. So there's many trade-off in the design phase, and actually one of the idea was to use a bomb to put on the surface of the asteroid, but scientists are so sensitive about the contamination of the soil. So what they said is that please make a very big artificial crater, but please don't contaminate the surface by the chemical compound brought from Earth. So it's a very difficult requirement, but our solution was then detonate in air and then accelerate and kinetic impact. On that way, the contamination gets minimum, and we can expect to have a very pure samples from the artificial crater. And one more important thing is that using copper. Copper doesn't exist in the natural world naturally, so that's why we chose the copper for the bullet.
Yeah, here, please.
Why did it take 4 years to arrive at the asteroid and only 1 year to return back?
Yeah, that's a good question. It's a matter of the different period of the Earth and the Ryugu, so the celestial geometry. So if you design the Earth to Ryugu trajectory and Ryugu to Earth trajectory independently, you can design like 1 year forward trip and 1 year return trip. But it is a sample return mission, so we have to go to Ryugu before coming back to Earth. So for that, within the limited mission time duration, so we have to take longer forward trip or longer return trip. And our choice was the longer forward trip to mitigate the risk. In that way, we can minimize the risk of the interplanetary cruise.
Are there any more questions? Yes?
I was just curious about how did you determine the mass of the sample that you collected? So OSIRIS-REx, they had mechanisms such as pirouetting or spinning around the spacecraft and then determining the mass based on that. So did you use a similar mechanism or determine the mass once you were on Earth?
Yes, actually we didn't have such mechanism on board, and we didn't have any strategy to measure the collected sample before the spacecraft actually returned to Earth. And there are many discussions about that, and we tried to install such kind of measuring mechanism, but we finally decided not to do so. And actually that works, I think, good, because you can only know the amount of sample after the spacecraft returns, and in that way, scientists can come with us
Dream.
until the Earth return. The final part is just a joke.
Please, there is a question here.
Could you explain an orbital mechanic point of view, how you reach the asteroid and how you land there and how you go back? Do you match the orbit of the asteroid? I don't know how you do it. It's very complicated, I think. And it's also the time delay, all these things you have to match.
Okay, so the asteroid, the ephemeris or orbit of the asteroid was determined beforehand through the telescope observation, or ground-based telescope observation, but it had only a very limited accuracy. So the spacecraft, once launched, it flew toward the asteroid direction, but but still the asteroid position has an uncertainty of about 500 kilometers. So when approaching to the asteroid, the spacecraft did the optical navigation, which basically observed the asteroid from the spacecraft on board camera to precisely determine the relative position of the spacecraft relative to the asteroid. In that way, we could reach the asteroid very precisely. And so the optical navigation is the key. And at the time of the proximity operation, the distance between Earth and Ryugu, or Earth and the spacecraft, is about 300 million kilometers, which corresponds to 20 minutes one-way light time. So it's not good for precise guidance, asteroid relative guidance. So we extensively utilize the autonomous guidance aboard the spacecraft.
Thank you. Last question. We're already a little bit over time. No last question. I have the last question. Thank you. That's good. Of course, this is the International Astronautical Federation, and I would like to know how the samples will be shared with the international community, and with how many institutes are you working for the scientific analysis of the samples?
Yeah, thank you for a good question. And now it's still in the initial analysis phase, and in this phase we are collaborating with 6 or 7 institutes, basically in Japan. But in the end of this year, we started to deliver to the international community, first to NASA for exchanging the sample with the Osiris-Rex mission, and I really hope Rex comes back to us. And the next year, we will start delivering to the general researchers worldwide through AO. So we basically we accept the proposal from the scientists and review it, and then selected some the good proposal, and then deliver to them.
Wonderful. I want to thank you for a really fascinating lecture. I think we all want to congratulate you for this award. It is well deserved. It was a fascinating lecture to see how you actually conquered the asteroid and how many decisions were necessary in order to bring the samples also successful back to Earth. A very complex mission, a lot of technology first, and we really congratulate you to your success, and we thank you for this wonderful lecture, and we are also really, really happy that you got this award.
Thank you.
Thank you. Please have me up. And if there is still somebody who has questions, Dr. Tsuda, I'm sure is here.